we will show you the simulation of our car park indicator system. Now, we will introduce to you our inputs. If the switch is pushed upwards, it represents the car entering the car park. If the switch is pushed downwards, it represents the car leaving the car park. The push button on the left is our reset button. The push button on the right is our clock button. We use 7 segments to display the number of lots available. This 8 LED represents the car park lots. If the LED is turned on, it is to indicate that the lot is free. This is our empty car park. As you can see, the 7 segment is displaying 8, which is the maximum number of lots available. Therefore, all of the LED is turned on. So now, we will show you how it works when a car enters and leaves the car park. When a car enters the car park, the 7 segment display will decrease by 1, which will then display 7, telling us that there are 7 lots left. At the same time, the LED lights will also decrease by 1. When another car occupies the lot, the 7 segments and LED keep on decreasing by 1 as shown. However, if we set it to out center state, it is telling us that a car is leaving the lot. Thus, the 7 segment and the LED will increase by 1. On my board here, we can see that there are 7 empty lots as the car has left the car park. At the same time, the LED tallies with the 7 segment. Next, we will show you what will happen if the car park is full. First, I will have to set the switch to in sensor state. I will keep on pressing the clock to indicate that there are cars entering the lot until there is no lot left. Shown on the 7 segment is the letter F. Also, none of the LED lights up as the lot is occupied. F is to tell the drivers that the car park is full. Now, we shall do our reset. When reset is activated, the 7 segment should display the latest status of free slots. As what we have, our latest number of lot is 5. For example, a car occupies the car park. If we were to reset it, the number shall remain the same. We will now explain to you our coding for 7 segment. Entity 7 segment is where we declare our variables. D3 to D0 is our input, A to G is our output. Under the architecture arc, we declare our signal input and signal output. Signal input is the vectors for internal, 3 down to 0 as we have 4 bits. Signal output is used in decoder statements, 6 down to 0 as we have 7 bits. There are a total of 16 bits as we have 4 inputs. 4 inputs is equivalent to 2 power of 4, which is 16-bit output. However, we only use 9-bit outputs. The 9-bit output is derived from the truth table. The remaining 7-bit output, we put it as F. At the bottom section is our output vector. It has to be separated to make individual pin output. For our LED coding, the code is very similar to our 7 segment. The only difference is that the binary is different. And the remaining 7 bits is based on our 7 segment code, where we set F for the remaining 7 bits. Therefore, LED is put to high to turn off the LED.
Now I'll be explaining to you the coding for the counters. Under the entity, we declared the input and output. The inputs are the sensor, clock, and reset. As for the output, it is Q. Now I will be explaining the main program. If reset is set to 0, then the count signal will show the latest slot available. And as for the falling edge, When sensor is at logic 0, the count signal will +1, indicating that the car is leaving the car park. But when it is at logic 1, the count signal will -1, indicating that the car is entering the car park.
This is our truth table for LED. The column here shows the number of LED that lights up. Right next to it, we have our inputs, D3, D2, D1, and D0. We use 4 inputs as we had to display 9 outputs. Moving on to the output, we use 8 outputs as we need 8 LED to indicate the availability of the lot. 1 is logic low, LED does not light up, while 0 is logic high, LED lights up. When it is on F, all LED is to be switched off. Thus, it is 1 1 1 1 1 1 1 1. Similarly to our LED, we use 4 inputs, except that for 7 segment, the total number of output is 7, which is A to G. The 7 segment lights up according to the number or letter we would like to display. So if it is F, the output A, E, F, G is to put to 0, which is logic high. The rest shall be put to 1, which is logic low. When sensor is low, it means that it is at the out sensor state. When the clock is pressed, the count will increase. For example, 0000 indicates F. For our situation, it tells us that the car park is fully occupied. Every time the clock is pressed, the count increases by 1. 1, 2, 3, and 4 until it reaches 8, the maximum number of lots available. Moving on, when the sensor is high, it means that it is at the in-sensor state. When the clock is pressed, the count will decrease. 0110, which is 7, to 0110, which is 6, and it will continue to count down to 0000, which is F. F display tells driver that the car park is full.